Hi everyone, welcome back. In today's video, we're going to be looking at how radiation affects your body. To start with, let's talk about what radiation really is. Radiation is everywhere and every day. It comes from the sun, your devices, bananas, and even the ground. Radiation can occur as waves or as a stream of particles. Radiation can be of high energy or low energy. High energy radiation is ionizing, which can hurt you. Low energy radiation is non ionizing and it cannot really hurt you. An example of low energy can be microwaves, and high energy could be gamma rays. So, if we zoom in and look at an atomic level, now, inside the atom, there is lots of energy inside the nucleus, which is the strong nuclear force which holds the nucleus together. Now, if the atom is stable, there is enough energy to keep it together forever. On a side note, in physics, this is the strongest force. Now, let's say an atom has too many or too few neutrons. In this example, there are too many neutrons, which is the yellow particle. Then that means that the strong nuclear force is unbalanced, and that leads to radioactive decay, which is radiation, to get the atom in a stable state. Radioactive decay is basically releasing energy from the atom to get stable. Now, there are three types of radioactive decay: alpha, beta, and gamma. Let's look at the first one here, alpha. Basically, over here, the nucleus releases two protons and two neutrons tightly bound together, which is basically a helium nucleus. Now, the alpha particle is a little bit heavier than the rest, and so it can travel smaller distances. Also, alpha particle is the highest ionizing radiation, so it is the most dangerous and causes the most internal damage. Now let's look at beta decay, which is of two types, positive and negative decay. This happens when there are too many neutrons. So here, the neutron of the nucleus turns into a proton. It decays itself into a proton and releases a high energy electron, which is the beta particle, and an antineutrino. In beta plus decay, there are too many protons, and so one of these protons turns into a neutron, and that releases a high energy positron, which is the antimatter counterpart of an electron, and a neutrino. Now keep in mind the beta particles are a little bit lighter than alpha particles, so they can travel longer distances. Now let's move on to gamma radiation or gamma rays. Now this is the highest frequency electromagnetic wave and can travel further than all the others, meaning beta and alpha. Here's a little review of all of the three types of radioactive decay. Now there is this special term called half-life. That is the time taken for half of the radioisotope to decay. This can range from a fraction of a second to billions of years. Here's an example of radioactive decay of radium-226. So what makes radiation so harmful? If someone has experienced acute exposure to ionizing radiation, this radiation can enter their cells and interact with the molecules and the cell. Now, this energy is enough to knock out electrons from the atoms and start a chain reaction where this electron goes to other electrons and knocks out their electrons. From here, it can go two ways. It can either bring changes in the molecular structure or it can damage the cell. For example, the H2O in our body, which is water, can turn into hydrogen peroxide, which is H2O2, just by this radiation, and that is not going to be good for us. Now let's look at what happens when the radiation damages our cell. Now if we rewind a little bit and go back to the part where we were talking about electrons knocking out electrons and causing a chain reaction, this would leave behind positively charged atoms, which are unstable. Now these atoms want to get stable and they will release energy. Now this energy is doing the damage. Now the main thing we're concerned about here is DNA damage, which could potentially lead to cell death and even organ failure later on. But another thing it could lead to is cancer. Now, cancer is often caused by DNA mutation, which can lead to abnormal cellular growth, which can threaten tissues and organs. Basically, in our cell, the DNA has two types of genes, and many others, but these are the two we're going to talk about: tumor suppressor gene and proto-oncogenes. Now, tumor suppressor gene, from the name, is the gene which helps reduce the chances of cancer and stops the cell from dysfunctioning. And proto-oncogenes do the exact opposite because they turn into oncogenes. Now, DNA damage can lead to the activation of these oncogenes and deactivation of the tumor suppressor gene, which can lead to this. The cell stops following the body's tissue growth regulation, and that can lead to a tumor because the cells are going to proliferate uncontrollably, like so. And if this tumor becomes malignant, it becomes cancerous and moves around the body, damaging surrounding tissues. Now let's look at another example and take a person in particular and see what happened to them. Marie Curie. She spent a lot of time near X-rays and she helped patients during World War I. This exposure to radiation and the exposure she had while her research, because she did a lot of research on radioactivity, this probably resulted to aplastic pernicious anemia, which led to her death. Now let me explain how this could happen through radioactivity. Let's start by looking at aplastic anemia. Bone marrows contain something called hemocytoblasts. This gets converted into myeloid stem cells and a lymphoid stem cell. The myeloid stem cell develops into RBCs, WBCs, and platelets. Now, this step is affected by radiation and disturbs the process. So, a person having this anemia would have low WBC, RBCs, and platelets. Now, here are the impacts of that. Now, let's look at pernicious anemia. This is caused by B12 and folic acid deficiency. Normally in the stomach, the parietal cells secrete a glycoprotein and B12 would naturally bind to this. However, when someone has an autoimmune condition whose risks are increased by radiation, the immune system would produce antibodies which would bind to the glycoprotein instead. So now B12 cannot be absorbed. Here are the impacts of that. So that could have led to the death of Marie Curie. In summary, we have looked at these things. Thanks for watching!